Namaskaram everyone. Welcome
Good
back
afternoon, madam.
all the students for another interesting session in mathematics. This is going to be a new topic from Mathematics 1A and it's mathematical induction. Students, induction is a process wherein you take so many examples and then in a systematic manner you come to the conclusions and prove a statement. In mathematics, we come across many statements. Some of the statements are true for some values of the variable involved in it. Some of them are true for many variables involved in it. We have seen linear equations and then quadratic equations and all, isn't it? When you substitute few values, some of the equations were true. When you substitute many values, infinitely many solutions are there for some. So in mathematical statements, there is a method which helps us in asserting, in proving whether the statement can be a generalized one and be taken for all the values of the variable involved in it when we consider the domain as a natural number set or positive integral set. Then how do we do that? We do that in a stepwise manner, which will be explained by our own PGT from PSMS Gavicharla. Sri Raja Prabhu Rampalli sir is with us today to take you on a journey in understanding what is mathematical induction and how do we use the principle of mathematical induction in proving the statement. Raja Prabhu sir.
Good afternoon, madam.
Mathematics from PSMS Gavicharla from Warangal Rural District. Before joining model school, he had lot of experience in working in private institutions, also in administration. We are very fortunate to have Raja Prabhu sir to handle mathematical induction. Students, this is an interesting topic and you will get a 7-mark question in your IP examination according to the existing pattern. So please understand the steps involved in it and try to practice more and more problems and whatever the instructions are given by sir during the course of our session. Raja Prabhu sir,
good afternoon, madam. Thank you, madam. Thank you very much.
Please
thank you.
Take over the session and it's over to you, sir. Thank you.
Thank you, madam. Thank you, madam. I'll try at my best level, madam. Thank you. Good afternoon to one and all. So this is Raja Prabhu, working as PGT Mathematics in Gavicharla, Sangamandal from Warangal Rural District. I'm very happy to talk to you all today. I want to share my view regarding this small topic, mathematical induction, with you all. So I hope all the children will be following me. So today's topic is mathematical induction. In our general life, or especially in sciences and mathematics, we have several concepts, several proposals, several theorems, some statements, etc. So whatever we follow till now, which was proposed in the past, so compulsorily there will be a certain proof for that. So after proving all the concept, then only we will generalize it everywhere. So in the same way, here in mathematics, to prove any mathematical statement or a theorem or a formula, whatever it may be, there will be different methods. So some of the different methods of proofs are, I think all of you know, just like direct method, indirect method, uh, inductive method, deductive method, or project method, or heuristic method, or proof by the demonstration, etc. So today I want to come to one of the proofs known as induction method. So what do you mean by induction? It is nothing but uh, coming from specific to generalization, or coming from a particular type to making it as a generalized. So that we are going to learn today in the form of mathematical induction. So firstly, mathematical induction means it is one of the technique which is used to prove a statement, a formula, or a theorem, whether it is true for every natural number or not. Every natural number or positive integer, nothing but starting from 1, 2, 3, 4, 5, and so on. Now let us see what is that today. This technique mainly involves two steps to prove any statement. So what are those two steps? Here, the step 1 known as the base step. It is nothing but it proves that a statement is true for the initial value. Initial value nothing but from where we are starting, especially in the field of natural numbers, from n is equal to 1. Sometimes basing on particular condition, the initial value may not be 1. It may be from 2 or from 3 or from 10 or from 100. That is depending on our conditions. And the step 2 is known as inductive step. It proves that if the statement is true for nth iteration or nth term, then it is also true for n plus 1th iteration or for n plus 1th term, up to n plus 1th term. So these are the two main steps of proving any statement using mathematical induction. So here there is a principle for mathematical induction. Now let's see actually what is that. The principle of mathematical induction is, so we are in pure mathematics now. So let P of n be a mathematical statement where n be a positive integer, then the statement is true for n is equal to 1. Nothing but we are verifying at the base step, that is nothing but in the starting, that is at first step known as n is equal to 1. That means proving that P of 1 is true or not. What is P of 1 means? We consider that P of n be the given mathematical statement. There will be a variable in that n. So substituting in the place of n1 and verifying whether it is true or not. If it is true for n is equal to 1, then the first step itself is finished. And the second step, if the statement is true for n is equal to k, where k can be any positive integer, then the statement also will be true for n is equal to k plus 1. So these are the two major steps of principle of mathematical induction. This implies the truth of P of k implies the truth of P of k plus 1. Means the P of n will become true, means when it is verified in these two steps, then the total statement will become true for all the natural numbers. Okay, now there are different steps to prove any mathematical statement by using the principle of mathematical induction. Okay, I'm trying to give those three steps. Here I already told you there are majorly two steps to prove any statement using mathematical induction. Here the first step is very clear, that just verifying for n is equal to 1 and nothing but the base step. And the second step can be classified into two ways. Okay, let us see one by one. Now the step 1 is known as the basis of induction, that is just proving whether P of 1 is true or not. And the second step, that is known as inductive hypothesis. In this, at the second step, just we will be assuming that the statement is true for n is equal to k or not. We have to assume. Okay, here depending on the problem, we can identify the two through our basic knowledge, through our past experience. We can identify whether the statement is correct or not. Okay, that you will become very clear when you are going through the problems. Okay, your children, you please try to understand. And the third step is inductive step, that is showing that the given statement is true for n is equal to k plus 1. Nothing but the statement p of k plus 1 is true on the basis of inductive hypothesis. So here the second step is classified into two steps again, that is second and three in this case, that is inductive hypothesis and inductive step. Here the major problem, major part of our answer of the problem will be in the third step for every problem. Okay, by going through the problems you can understand. Children, you also remember here, this mathematical induction is one of the methods of proofs. As I told you, this is one of the method of the proof by the process of verification. Means just we are verifying at different levels and we are proving it. According to the principle of mathematical induction, to prove any statement is true, we have to verify at three levels. Those are the three levels what you are seeing on the, what you are observing on the screen now. One is the basis of induction, the second one is inductive hypothesis, the third one is inductive step. So basis of induction means just verifying for n is equal to 1, that is p of 1. And in the second step, we need to assume whether the statement is true for any value of n equal to k or not, that is verifying for p of k is true or not. P of k in the sense substituting in the statement in the place of n k and verifying. Okay, in the same way the third step is here p of proving that p of k plus 1 is true means we are verifying up to the k plus 1th term whether the statement is correct or not. Okay, children, now let us see. So this is the main process of proving any statement using the principle of mathematical induction. So here I am giving you a problem. So you try to understand one of the problems so that you will become easy to know the concept. Okay, here I gave you a problem, students. The problem here is using mathematical induction, prove sigma 2n minus 1 is equal to 1 plus 3 plus 5 plus 7 and so on up to the nth term, that is 2n minus 1, which will be equal to n square. Students, you might have noticed the problem here. All the odd numbers are given starting from 1 up to the nth term, that is 1, 3, 5, 7 and so on, some of them. So I think you might have noticed a formula for sum of all the odd numbers in your 10th class, that is in progression chapter. It is one of the arithmetic progression. So you might have derived that formula also by using arithmetic progression concepts. So sum of the first n odd natural numbers will be is equal to n square. Now here we are going to prove it by the process of verification. Also let us identify the symbol sigma here. Sigma is for sum. 2n minus 1 is nth term. So using sigma, only the nth term is written here, that is nothing but a chart form of the total expansion, so which is known to you already at your lower classes. Okay, anyway, now I'm coming to the actual concept, how to prove this. Okay, for that, as I told you, to prove this statement, we have to verify in 3 cases. Okay, for our convenience, firstly, in almost in every beginning of the problem, let us consider the given statement as some p of n. So here I consider let p of n is equal to the given statement, that is 1 plus 3 plus 5 plus and so on up to 2n minus 1, which is equal to n square. Okay, now to prove this, what we have to prove? We need to prove the statement is true for every natural number. There, for every natural number, nothing but for any number of terms. For any number of terms means, suppose if you consider only first term is 1. Sum of one term nothing but 1 itself. In the right hand side, n square is there. In the place of n, write 1 square becomes 1, which is true. Suppose if you want to verify up to 2 terms, 1 plus 3. 3 the second term, 1 plus 3 becomes 4, and substitute in the right hand side in the place of n 2, 2 square becomes 4, 4 equal to 4, yes, it is verified. In the same way up to the third term, 1 plus 3 plus 5, which is equal to 9, in the place of n when you substitute 3 in the right hand side, that is 3 square, also 9, so it is verified. In the same way we have to verify at 3 stages. Okay, that I'm going to prove now. So firstly, step 1. What is step 1? We have to verify by substituting in the place of n1. So P of 1. So what is that? There are two parts in the given statement, LHS and RHS. So first let us check for LHS. Substitute n is equal to 1 in LHS. Then what it becomes? The nth term of LHS is 2n minus 1. So in the place of n, when you write here 1, you check here 2 into 1 minus 1. 2 into 1 is 2, minus 1 is 1. Okay, LHS became 1. Or blindly you can say here LHS substituting n is equal 1 nothing, but just first term. Okay, of course in this problem the first term is 1. In different problems the first term may not be 1. It can be different. You can just to verify what is the first term here, or you can substitute n term in the place of n1, you get the same, one other is same. Okay, children. Now let's go for RHS. What is RHS here? That is n square. RHS here is n square. Therefore, substitute n is equal to 1 in the place of n1. Okay, that is n square nothing but in the place of n, when you substitute 1, 1 square is also 1. Now it is very clear that LHS is 1 and RHS is also 1 by substituting in the place of n1. That means here we got that LHS is equal to RHS, that is 1. Therefore, P of 1 is verified. Therefore, P of 1 is true. So, children, I hope you are following me. Okay, this is the first step. And let's go for the second step. What I told you regarding the second step nothing but, that is nothing but consideration or assumption. So, let us assume in the second step, that is, assume that the statement P of n is true for some positive integer k, that is n is equal to k. So you know the given statement up to the nth term is 1 plus 3 plus 5 plus 7 and so on, up to the nth term will be 2n minus 1, which is equal to n square. Now here I am substituting n is equal to k, then it becomes the nth term will be 2k minus 1, which is equal to k square, just substituted in the place of nk. Now here this is the only induction hypothesis, so we need to assume that it is true for n is equal to k. There are some special cases where it may not be true in the middle for n is equal to k. Okay, those special cases also we will try to see. Okay, this is a beginning problem. I hope that for the understanding purpose only, I have considered one of the easiest problem now. So in the coming problems, you can understand everything. So you please follow me. Okay, now coming to the third step. The third step here is we need to prove that P of k plus 1 is true. What is P of k plus 1? Just substituting in the place of n k plus 1. Then here the nth term is 2n minus 1. You follow, children? I think you are following me. The nth term here is 2n minus 1, whereas the kth term is 2k minus 1. Now we want P of k plus 1. To get P of k plus 1, now we have to find the kth term, that is tk plus 1. Means in the place of k, write k plus 1 here. 2 into k nothing but k plus 1 minus 1. When you simplify this, 2 into k is 2k plus 2 into 1 2 minus 1, which becomes 2k plus 1. Here is 2 into 1 is 2, 2 into 1 is 2 minus 1 becomes plus 1, that is 2k plus 1 is the k plus 1 the term of that sequence or series given. Okay, next what to do? We have to write the statement up to the k plus 1th term. Now, up to the kth term we have, that is equation 1. Up to the kth term here we have, that is represented by here equation 1. Now to get P of k plus 1 nothing but adding this k plus 1th term on both sides of this equation 1. So let's see here, on both sides of equation 1 is added by 2k plus 1. Okay, then let us see what happens here. Now P of k plus 1 is, this is the important step that everyone has to understand. So please children concentrate here at this step. Here 1 plus P of k plus 1 is equal to 1 plus 3 plus 5 plus 7 and so on up to the kth term, it is 2k minus 1. Now I have written here up to the k plus 1th term, nothing but k plus 1th term here is 2k plus 1, which is added here. Then the total expression becomes here P of k plus 1, which is equal to up to the kth term, it is k square, and this 2k plus 1 is added. It should be added to the right hand side also. Okay, now let us see here one more important concept here to prove this. In the beginning of the problem itself, we can understand, or we can guess what we are going to prove, what we have to prove at the end. What we have to prove means at the end, in the right hand side, in the place of n, we have to get k plus 1, because we are verifying up to the k plus 1th term. So see children, here what is this? This right hand side here is k square plus 2k plus 1. It is very clear that it is in the form of just like a square plus 2ab plus b square, where b value is 1, b square is also 1, 1 can be considered as 1 square, and the middle term here is 2k, 2k also can be written as 2 into k into 1, so which can be written in the form of a plus b whole square, a nothing but k, b is 1, so it can be written in a factorized form, that is k plus 1 whole square. So we got this now. Means here in the place of n square, we got k plus 1 whole square, means n is replaced by k plus 1, means here it is very clear that P of k plus 1 is also becoming true, means P of k plus 1 is also verified. Therefore, now here the statement is verified at 3 stages, at 3 steps. That is from equation, from first step, it is verified by substituting n is equal to 1. Also at the second step, we assume that it is true for n is equal to k, and at the third step is verified for n is equal to k plus 1. So here our principle indicates that if any statement is true for n is equal to 1 and n is equal to k and n is equal to k plus 1, then the total statement will be true for any value of n. So according to that principle, the principle of mathematical induction, here in this problem from steps 1, 2 and 3, by the principle of mathematical induction, we can say that P of n is true for all the natural numbers. So as it is true for all the natural numbers, then we can say that the given statement is correct. Hence the problem is proved by the process of verification. Now this is the main process of proving any problem for using mathematical induction. Okay children, here this is the main process. Now let us see, here I told you just now, okay, here in every problem all the methods are not applicable in general. Okay, here also I told you now there are 3 different steps to prove any mathematical statement using the principle of mathematical induction. That means here invariably all the 3 steps must be considered. Okay, suppose sometimes in some of the cases the first step may be failed, whereas the other 2 steps may be followed, or sometimes the second step may be failed and first and the third step may be followed, or sometimes the third step may be failed, first and 2 cases may be followed. That means if any one of these 3 cases is failed, then compulsorily the statement is not true, even though the other 2 steps are correct. Okay children, so we have to consider all the 3 cases to prove any statement when we are using the principle of mathematical induction. Here I am giving you a small example which is taken as a special case. Let us see one of the simple problem once again. Here let's see children, almost the same problem, the previous problem what I gave you just now. P of n, that is equal to 1 plus 3 plus 5 and so on up to 2n minus 1, which is equal to given as n square plus 5. Actually it is up to n square only in the previous problem. Now here something is added. Now in this particular case it can be proved at second and third stages, but it fails only in first case. You see children, here suppose if you write in the place of n1, just now we checked that 2n minus 1 LHS is equal to 1, 2 into 1 2 minus 1 is becoming 1 here, but whereas in the right hand side, in the place of n, when you write 1 square plus 5 is becoming 6, whereas 1, the first term 1 is not equal to 6, nothing but it is failing in the first case. Of course, but it follows or it satisfies the second and the third cases. Okay, here the step 1 is becoming failed. Now suppose if the p of the statement is p of n is equal to this one. Now the kth term here is 2k minus 1. The nth term is 2n minus 1. Now I'm going for the third step by verifying for n is equal to k plus 1. Let us see. Just now I told you orally by verifying n is equal to 1, where it is failed, but it satisfies up to the k plus 1th term. How it is possible? Now once you check, the kth term is 2k minus 1. Therefore, the k plus 1th term will be substitute in the place of k plus 1. It becomes 2k plus 2 minus 1, which is equal to 2k plus 1. So usually to verify up to the k plus 1th term, we have to add the k plus 1th term on both sides of that equation. Okay, let us see here. I have written this expression up to the k plus 1th term. That is p of k plus 1 is equal to 1 plus 3 plus 5 and so on up to 2k minus 1 plus 2k plus 1. Here 2k plus 1 is added to the left hand side, so that it should be added to the right hand side also. So the right hand side actually up to the kth term it was k square plus 5. Now here 2k plus 1 is added. Now it becomes k square plus 2k plus 1 plus 5. Just I replaced these two terms. So you please don't confuse. Nothing is there here. 1 is written here and 5 is written here. Now children, see what is this? K square plus 2k plus 1 can be written as k plus 1 whole square, and plus 5 is I stays. Okay, which will be in the next step. Up to this part, up to k square plus 2k plus 1 is written as k plus 1 whole square plus 5. Now see what is this? It is in the form of n square plus 5, where in the place of n there is k plus 1. Means it is verified. It is verified for up to the k plus 1th term. Means it is following the third step. And the second step, this assumption, we can assume that it is true for n is equal to k. Means this particular problem is following the second step and the third step, whereas it failed the first step. It failed the first step. Just now we checked it. What is the first step here? When we substitute n is equal to 1 or k equal to 1, the LHS is 1, whereas RHS is becoming 1 square plus 5, that is 6, which are not equal. 1 is not equal to 6. Therefore, this statement is not correct for all the values of n. Therefore, the statement is not true. We cannot prove it because the statement is not correct for all the values of n. Even though it satisfies in two cases, n is equal to k and n is equal to k plus 1, as it fails in the first case, the statement is not true in all the cases. Therefore, to prove any statement in applying the principle, invariably all the steps must be taken, must be considered. Then only we can come to a conclusion that the statement is true in all the cases. Okay, you please follow this special case. Okay, now I hope you are following me. Okay, I'll be very sure that by doing one more problem, all the students will be perfect to prove any mathematical statement by using the principle of mathematical induction. So children, I'm coming to another problem. Let's identify this. Already have some concept now. So use that concept and you please concentrate on this problem. Then easily you can understand or you can prove yourself any kind of other problems, other such problems. Okay, children, here I gave you one problem. Using mathematical induction, prove sigma n square is equal to 1 square plus 2 square plus 3 square and so on up to n square, which is equal to n into n plus 1 into 2n plus 1 whole divided by 6. Children, you might have noticed what problem is given here. That is the sum of the squares of the first n natural numbers. Already you know that formula at your 10th standard. That is nothing but sigma n square, which is equal to n into n plus 1 into 2n plus 1 by 6. Okay, now we are going to prove this by the process of verification, that too by using the principle of mathematical induction. So already you know, to prove any statement, there will be 3 steps. Now, before you start the problem, for our convenience, we need to consider the statement as the P of n. P of n is equal to the given statement, that is 1 square plus 2 square plus 3 square and so on up to n square, which is equal to n into n plus 1 into 2n plus 1 by 6. Now we need to prove that this is true for any value of n, means up to the first term or up to the second term or up to the third term or up to the 10th term or up to any term, any number of terms, that it is true. Okay, we can't verify for all the terms 1 to 100 or 1000 or like that. So we have to verify only at these three stages. If it is true for these three cases, then compulsorily it will be true according to the principle of mathematical induction for any value of n. Okay, that's what we are proving now. Okay, for that, what is the first step? We have to prove that it is true for n is equal to 1. Nothing but P of 1 is true, means substituting in the place of n 1 and verifying. Okay, what is LHS here? The nth term of the LHS is n square. So when you write in the place of n 1, then what happened here? N is equal to 1 means n square, 1 square also 1. Okay, also check RHS. What is RHS here? The main formula, that is n into n plus 1 into 2n plus 1 by 6. So in this also you substitute in the place of n 1. Okay, see children, what happened here? N is equal to 1. Here 1, n plus 1, 1 plus 1, 2n plus 1. In the place of n I have written 1, 2 into 1 plus 1. Okay, it is very ordinary simplification. I hope everyone will follow that. 1 is ISTs. Here 1 plus 1 is 2. And 2 into 1 is 2. Plus 1 will be 3. So it is now 1 into 2 into 3. Please follow the cursor, what I am using here. 1 into 2 into 3 is 6. 6 divided by 6, which is equal to 1. So it is very clear now. Our LHS is 1 and RHS is also, we have got 1. Therefore, it is very clear now, by substituting n is equal to 1, it is satisfied. Nothing but it is verified. Therefore, LHS is equal to RHS is equal to 1. Therefore, now P of 1 is true. Means the statement is true for n is equal to 1. So this is the first step. Okay, now going for the second step. Children, I hope you are writing the notes. You please try to note down the notes when the explanation is going on. So without notes, again, it will be a lot of confusion for you. So children, you please be active and try to be alert. So try to note down immediately. Okay, I'm coming to the second step of this problem. What is the second step? That is inductive hypothesis. We need to consider that the statement is true for some positive integer k, where k is also positive integer, nothing but a natural number. Okay, therefore, that means here verifying up to the kth term. So P of k will be equal to 1 square plus 2 square plus 3 square plus and so on up to k square, which will be equal to k into k plus 1 into 2k plus 1 whole divided by 6. Now we have to prove this. So already we have assumed it. This is nothing but the second step. Okay, the main process will be in the third step. Okay, here for our convenience, you consider this second step as equation 1. Okay, which we are going to use while doing the problem. Okay, we need to prove that now P of k plus 1 is true at the third step. So what is P of k plus 1 now? That is nothing but up to the k plus 1th term. For that, you identify what is the k plus 1th term. Kth term is k square. K plus 1th term means right in the place of k, k plus 1. Then kth term will be k plus 1 whole square. Okay, now to get P of k plus 1, usually we have to add k plus 1th term on both sides of that equation 1. Okay, let us see what is it. See children, what is equation 1 now? That is P of k. It is very clearly indicated. I hope you are following that. Okay, now I'm adding k plus 1 whole square on both sides of that equation 1. Then it becomes P of k plus 1 is equal to 1 square plus 2 square plus 3 square and so on up to k square plus k plus 1 whole square is equal to, the right hand side up to the k term is k into k plus 1 into 2k plus 1 by 6. Now up to the k plus 1th term, nothing but plus k plus 1 whole square is also added. Now the main process is here now. Actually, we are going to verify whether the statement is true up to the k plus 1th term or not. For that, what to do? Here, small simplification steps. Okay, just like factorization process. Here I'm following the factorization process. Okay, there are two terms in our RHS in P of k plus 1. This is the first term and k plus 1 whole square is the second term. Children, I think you are following that there is a common term in both of these two terms, that is k plus 1. K plus 1 is in common. So taking that k plus 1 as common, then in the first term, the remainder terms are k into 2k plus 1 by 6, which is here. And in k plus 1 whole square, when one k plus 1 is taken out common, the other k plus 1 is left. So that is written here. Now, here there is a fraction within the bracket. So try to simplify within the bracket first. Okay, what simplification that we can do? Just like doing LCM. LCM here is 6. So children, follow that step. Okay, by doing the LCM, here you got now the denominator is 6. So the numerator becomes 2k square plus k plus 6k plus 6. Here there is small inconvenience. Let me once go back, please. Just to see. Here, children, follow this step. 6 is the LCM. By doing LCM 6, here the numerator will be k square plus k square into 2k becomes 2k square plus 1 into k is k plus 6 into k 6k plus 6 into 1 is 6. So only that step is written in the next. Yes, children, I think you followed right now. The numerator here is 2k square plus k plus 6k plus 6 divided by 6. Now k plus 6k is 7k. That is written here. Right now, here it is just like a quadratic polynomial or quadratic expression. Now we have to factorize this. So students, you make a note of it, please. Every student has to be perfect in all the basics. Among all those basics, the factorization process is also very important thing, which you get always in every problem, everywhere in all the chapters. Therefore, so children, try to be perfect in that first. Okay, I think you know this process of factorization. First take the first another thing, well, the coefficient of k square, that is 2, and the constant term is 6. You find the product of these two, that is 2 into 6 is 12. Now again resolve the 12 into two factors such that their sum will be 7. Okay, so factorization of 12 will be 3 into 4. So I'm writing this 7k is 3k plus 4k in the next step. Okay, children, just 2k square plus 7k can be written as, the 7k can be written as 4k plus 3k plus 6 is ISTs. Now these three terms are written into 4 terms. Okay, that is for the process of factorization. Now consider the first two terms of this. First two terms. What are they? 2k square plus 4k. Now in this you take out the highest common factor as common. The highest common factor will be 2k. 2k is here and also in this 2k. So take a 2k common, and in this the common factor will be 3. Take out 3 common. Okay, which will be indicated in the next step. So this k plus 1 is ISTs. This k plus 1 is ISTs. Now here 2k square plus 4k. In this I have taken out 2k common. The remainder in this is 1 more k, and remainder in this is 2. So 2 plus 2, k plus 2. Now it is 2k into k plus 2. The other two terms can be written as, by taking 3 common, it is 3 into k plus 2 whole divided by 6 is ISTs. Now children, it is very clear. Again k plus 2 is in common among these two terms. Okay, here k plus 2 is in common. So take out that k plus 2 common. Then what you will get here? K plus 2 into, here left out term is 2k. This plus is ISTs and plus 3 is ISTs. Now it is factorized. Okay, after the factorization, as already told you, you know in the beginning itself that you can guess our final answer, that what you are going to prove. Okay, only the thing here we have to get in the place of n k plus 1. In the place of n k plus 1. Now see children here, a small step. This k plus 1 is ISTs, k plus 1 is here, and this k plus 2, in this k plus 2, this 2 is written as 1 plus 1, just 1 plus 1. And 2k plus 3, this 2k plus 3, in this this 3 can be written as 2 plus 1. So 2k plus 2 plus 1, in that you take a 2 common, then you will get this term 2 into k plus 1 plus 1. So here now it is very clear that this step is in the form of just like n into, where n is equal to k plus 1, n into n plus 1 plus 2 into n plus 1 whole divided by 6. So now it is very clear that our RHS part is in the form of given RHS, just in the place of n there is k plus 1, means this statement is true for n is equal to k plus 1. That means P of k plus 1 is verified, means the third step is verified now. So according to the principle of mathematical induction, the given statement is verified in all the three cases by substituting n is equal to 1, and in the second step assume that it is true for n is equal to k, and also by substituting the place of n k plus 1, it is verified. So as it is true in all the three cases, the statement will be true always for any value of n. Therefore now the statement is proved, nothing but sigma n square is equal to 1 square plus 2 square plus 3 square and so on up to n square is equal to n into n plus 1 into 2n plus 1 whole divided by 6. Hence it is proved. Okay children, now this is about the second problem what we have proved. Children, here there are some different types of problems to prove using the principle of mathematical induction. Here I want to take some other type of problem, that is to test the divisibility. Okay, here the problem is on the screen. You follow that. Using the principle of mathematical induction, prove 3 into, the dot indicates here into, 3 into 5 to the power 2n plus 1 plus 2 to the power 3n plus 1 is divisible by 17, where n belongs to n, nothing but natural number. N can be any natural number or any positive integer. Okay, how to prove this? Here also we have the same procedure, that is just verifying at three cases. The first one is, okay, as usual, for our convenience, let us consider P of n is equal to the given statement as it is, that is 3 into 5 to the power 2n plus 1 plus 2 to the power 3n plus 1 is divisible by 17. Consider that as P of n. It is only for our convenience. And we have to prove that it is true, means P of n is true for all the natural numbers. Okay, coming to step 1. What is step 1? We have to prove P of 1 is true. That is by substituting n is equal to 1. Substituting n is equal to 1. You children, you please follow. Means in the power there is n. Therefore, simplify in the place of n 1 here. Okay, 3 into 5 to the power 2n plus 1, nothing but 2 into 1 plus 1 plus 2 into 2 to the power 3 into 1 plus 1, which is equal to, what is that? 3 into 5 to the power 3. Here 2 into 1, 2 plus 1 is 3, and whereas 2 to the power 4, this 4 is 3 into 1, 3 plus 1 becomes 4. So it became, now it's a very ordered simplification, 3 into 5 cube. 5 cube nothing but 125 plus 2 to the power of 4 means multiply 2 by itself 4 times, then you will get 16. 2 power 4 is 16. And 3 into 125 plus 16 will be 375 plus 16. 3 into 125 is 375 plus 16 is IST. Okay, which is equal to 391. You see children, this 391 is divisible by 17 or not. What do you mean by divisible by 17? If 391 is a multiple of 17, then automatically we can say that 391 is divisible by 17. Okay, this 391 can be written as 391 can be written as the product of 17 into something, you can check 17 into 23, which is equal to 391, or you just divide 391 by 17, then automatically you will get the quotient 23. So as the 391 is written as the product of two factors, one is 17 and the other factor is 23. Therefore, I70 is one of the factor of 391, then 391 is divisible by 17. So here we have to prove that 391 is divisible by 17 or not. Means by substituting n is equal to 1, we verified now it is, the given statement is divisible by 17. That means here P of 1 is becoming true. So therefore, P of 1 is divisible by 17. Therefore, the statement is true for n is equal to 1. Now, this is the first step. Now, let us go for the second step. Okay, what is step 2? In that also, like previous problems, we have to assume. We have to assume that the statement is true for n is equal to k, where k is greater than or equal to 1 and any positive integer. Means the statement P of k, that is 3 into 5 to the power 2k plus 1 plus 2 to the power 3k plus 1 is divisible by 17. Children, you understand one thing. If any number or any expression is divisible by something, means that expression can be written as that something into some other thing. For example, suppose, any example, suppose let us take a number 20. 20 is divisible by 5, we know. Means 5 is a factor of 20. How can we prove that? What step can we give to know that 20 is divisible by 5? Means 20 can be written as 5 into something. That something here is 4 now. 5 into 4. So 20 can be written as 5. The product of 5 into something, then 20 is divisible by 5. Now here also same thing. The expression 3 into 5 to the power 2k plus 1 plus 2 into 3k plus 1 is divisible by 17. Means the expression 3 into 5 to the power 2k plus 1 plus 2 to the power 3k plus 1 can be written as 17 into something, because we assume that it is divisible by 17. So you see here, this expression can be considered as 17 into something. That something I considered it as t, where t can be any natural number again. It is from the set of natural numbers only. So this expression is taken as 17t. Okay, next what to do? Here, while doing the problems, children, here we require one step. So for that, let us solve for this now. From this above expression, that is 3 into 5 to the power of 2k plus 1 plus 2 to the power 3k plus 1 equals 70t. From this, you solve for this. What is that? 3 into 5 to the power of 2k plus 1 is equal to, just to bring this term, that is 2 to the power 3k plus to the right hand side, then it becomes 17t minus 2 to the power 3k plus 1, and name it or consider this as equation number 1. We are going to use this in the middle of the proof. Okay, then continuation of that. Okay, now step 2 is over, that we assumed. Next, coming to step 3, where the important process involves in this. Okay, that is to prove P of k plus 1 is true. Means in the place of k, we have to substitute k plus 1 and check. Okay, what is P of k plus 1? You know from the previous steps, P of k, in the place of k, just I substituted k plus 1 to get P of k plus 1. That is now 3 into 5 to the power of 2 into k plus 1 plus 1 plus 2 to the power 3 into k plus 1 plus 1 is divisible by 17. Now we have to prove this. So to prove that it is also divisible by 17 means you try to express this total expression, that is P of k plus 1 as something into 17 or 17 into something. Then we conclude that it is also divisible by 17. I'm trying for that. Okay, what to do for that? Let us take this P of k plus 1, a small simplification steps here. Follow, children. Only the simplification here is only in the power. 2 into k plus 2, that is 2k plus 2 plus 1 becomes 3. And here 2 to the power 3k plus 3 into 1, 3 plus 1 becomes 2k plus 2 to the power 3k plus 4. Okay, next what to do? Here, small other simplification here. you split these three i's. 3 can be written as the sum of 1 and 2. So 3 is written here 1 plus 2, and 3k plus 4. This 4 can be written as 1 plus 3, 1 plus 3. Okay, a small change you need to recognize here. Now let's see. Here, this is in the form of just like some a to the power m plus n using the laws of indices, which can be written as a power m into a power n. Means it is now 3 into 5 to the power 2k plus 1 and 5 to the power 2. That is 5 square is written separately by separating the bases here. Here also the same thing. It is 2 in the form of a to the power m plus n, which can be written as a power m into a to the power n, where m is 3k plus 1 and n is 3. So this term can be written as 2 power 3k plus 1 into 2 to the power 3. Now see children, what is this? 5 square is 25 and 2 cube is 8. Just simplify that and write in the next step. So it is now, in the place of 5 square there is 25, in the place of 2 cube there is 8. Then it becomes, okay, now here I'm going to use something from equation 1, which we considered in the previous step. What is equation 1? I have written here once again. That is 3 into 5 to the power of 2k plus 1 is considered as 17t minus 2 to the power 3k plus 1. This we named as equation 1, which is written here. Students, you can notice in this step here, in p of k plus 1, there is 3 into 5 to the power 2k plus 1. Okay, in the place of this, you can substitute or you can replace that by 17t minus 2 to the power 3k plus 1. Okay, then what you get here? Okay, a very simple step, children. There is no confusion at all. Please follow this. 3 into 5 to the power of 2k plus 1 is replaced by this. That is from equation 1. I hope it is very clear to you all. Into 25 is ISTs, plus is ISTs, and the other part is ISTs, that is 2 to the power 3k plus 1 plus 8. Now here, this single term is written in two terms, that is 17t minus 2 to the power 3k plus 1. Here into 25 is there. Now I am trying to multiply these two terms by 25 because there is product in between them. So it will be 25 into 17t minus 25 into 2 to the power of 3k plus 1 plus this part is also ISTs. Okay, now you identify, you can notice that here is a common term, children. That is 2 to the power of 3k plus 1 is here and 2 to the power of 3k plus 1 is here also. So which is common, and the coefficients are different. When there are common terms like this, then you just add the coefficients, okay, which is shown to you already in the next step. Yes, the same step is carried forward here. Now you see here, this is minus 25 plus 8. For the understanding part, your children follow me. Suppose you consider this 2 to the power of 3k plus 1 as some x. Here also x. Now this is minus 25x plus 8x. Minus 25 plus 8x becomes minus 17. The difference of these two, from minus 25 plus 8 is minus 17. X nothing but that is 2 to the power 3k plus 1, which is a very simple step. So I think I do not require much more explanation for this. I hope you might have understood this. Okay, now what you got here finally? This is 25t minus, sorry, 25 into 17t minus 17 into 2 to the power 3k plus 1. What is our intention actually? We are going to prove that this is divisible by 17. So that we have to express the given expression as 17 into something. Now it is very clear. There are two terms in this. Among these two terms, 17 is in common. 17 is in common. Therefore, take out the 17 common. Then what is remained here? 25t. 25t is here. This minus is IST, and then this remaining term in this part is 2 to the power 3k plus 1. Yes, children. So now this is expressed as 17 into something. Now once you think of what is this something, here t and k are natural numbers. When t is natural number, 25 into t also will be natural. And when k is also natural, 3k plus 1, 2 to the power 3k plus 1 also will be a natural number only. Now difference of two natural numbers is also a will be an integer. It will be an integer. Now 17 into an integer will be always an integer. Nothing but here. So for every k comma t belongs to n, this 25 t minus 2 to the power of 3k plus 1 also will be a natural number. Therefore, consider this 25t minus 2 to the power of 3k plus 1 is some m. Then it will be that expression that can be written as that p of k plus 1 can be written as 17 into m, where m is this one, 25t minus 2 to the power 3k plus 1. Okay, now it is 17m. What is 17m? It is nothing but the multiple of 17. 17 into something is written. Therefore, it is known as multiple of 17. Okay, therefore now the 17m is divisible by 17. 17m is divisible by 17. 17m nothing but that is p of k plus 1. So p of k plus 1 is divisible by 17. Means this is verified for n is equal to k plus 1 also. Therefore now this p of k plus 1, that is 3 into 5 to the power of 2k plus 3 plus 2 to the power of 3k plus 4 is divisible by 17. That means this statement is verified for n is equal to k plus 1, means p of k plus 1 is true. So this is the third step. Now, therefore, according to the principle of mathematical induction, from steps 1, 2 and 3, by the principle of mathematical induction, the statement is true for all the natural numbers. Therefore, we can say that finally, we can conclude that 3 into 5 to the power of 2n plus 1 plus 2 to the power of 3n plus 1 is divisible by 17. So this is the proof of the third problem, the problem based on divisibility. Okay, children, here there are some other different type of problems. If time permits, we will see in the next class. And just let us review once again what we have discussed today. That is, yes. So today just I covered a very small topic based on mathematical induction. Children, it is also very useful for the examination point of view. You will get compulsorily one 7 marks question in this very small topic. So you please follow that. And just today I covered only one small topic. Once again, just let me review that. That is the principle of mathematical induction. That is, children, you review what is mathematical induction. The principle of mathematical induction is, if p of n is a mathematical statement, and if it is true for n is equal to 1, and it is true for n is equal to k, and it is true for n is equal to k plus 1, means when the statement is verified at these 3 steps, then compulsorily, automatically the statement will be true for any natural number. So this is only the concept what I have reviewed today. So children, you try to understand the concept once again. Let us try to concentrate on all the problems. I want to give you a few more problems for the practice. So children, you practice today. If at all you get any doubts, again, you can contact your regular teachers who can help you always. So you please note down these problems for the practice purpose. And then I hope you will do all these. Just one more small point, children, here. In some of the problems what I gave you now, in second, third, and fourth problem, it is clearly just indicate only up to nth term like that, up to the nth term like that, where the nth term is not given. But in the problems which I considered in those problems, nth term is given. But you can understand how to find the nth term also. You see, children, suppose in second problem, this is an arithmetic progression. The nth term here is, nth term of an AP is a plus n minus 1 into d. Okay, you can identify that very easily. And whereas in fourth problem also, see children, the first term is up to 1 square, the second term is up to 2 square, third term is 1 square plus 2 square plus 3 square, and so on like this. The nth term will be automatically 1 square plus 2 square plus 3 square, and so on up to n square. So that is nothing but sum of the squares of the first n natural numbers. Already know that formula, that is n into n plus 1 into 2n plus 1 divided by 6, like that. So you follow those concepts basing on your previous knowledge and try to follow that. So I hope you all are perfect in this small topic what I have taken today. So finally, I thank one and all for giving me this great opportunity. So thank you one and all. Thank you, madam, for encouraging me in all these aspects. Thank you one and all. Thank you very much, madam. Thank you.
Thank you, Raj Prabhu sir. It was a wonderful
Thank
session.
you. Thank you, madam. Thank you, madam.
And students will definitely get benefited out of it. I'm sure they will do all the problems that you have given for practice. And you have given them different examples, taking up like divisibility issue, then also series problems. Students, you please revisit the same session on the YouTube channel. And if you have still any doubts, as sir told, you can contact your regular teachers, you can get your doubts clarified, or you can post them in the chat box. We will also address them in our next session. Thank you, Raja Prabhu sir.
Thank you, madam. Thank you, one and all. Thank you very much.
Namaskaram, everyone.
Thank you.